Hi, and welcome to topic 9, which is interactive programming. And this is about where we look at the type of the main program. You've seen some of that in the starter code I've given you. So it's like the main program in anything really. It's the starting point and so on. And specifically, what we look at are the different types that indicate that something is performing I/O, or what we call an action. Okay, so we'll get started on it. And okay, so to date, we've seen how Haskell can be used to write batch programs or little functions. So what you have is you have your inputs or your arguments into the function, you have your program or your function, and you have outputs. And the action of the function can be written simply as a relationship, if you like, between the input and the output. There is nothing else. Okay, so, but Haskell is a pure language, but we do live in the real world. So we need to be able to say, yes, all of that is function, 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 but how are we going to reach out to the real world? And basically, we allow, we're going to see how we take in input from the screen or even from files, CSV files and so on, as you've seen, and that we can send out stuff to the screen. But in that case, right, the way we describe that in Haskell is that it's the outside world is coming in. We're changing something in the outside world. Okay, so we're writing to the screen. We can also change state, but we're not going to look at that at the moment for the assignment and so on. Okay, so what we're going to look at is the difference between the way input output is dealt with or mentioned or defined in Java and in Haskell. So the first thing we look at is mystery 1. So what is mystery 1? It's not that much of a mystery, but we take in two values, and we take in two values, val1 and val2, and we add those to tree and square it. Okay. Now, another one is mystery 2. And the point here is, right, if you look at the method heading, they're the same in both cases, the very same. I mean, we've called it mystery 1 and mystery 2, but apart from that. And val3 is 3 in the first one, so always it's a value of 3 that's there. Okay, in the next one, we do set off val3 is equal to 3, but we try to read in another val3. Okay, so we try to do that. We're just surrounding with try and catch and so on. So we'll return val1 plus val2 plus val3. Now the difference in the two of these is both of them have the same signature, but mystery 2 depends on the outside world. And specifically, if I call mystery 2 4 or 5 today and tomorrow, I might get different results. And the whole point of it's a thing called non-determinism, and there's a reason why that is non-deterministic, because there's another input coming in from the outside world. But we look at that and see, well, we need to be more upfront about how, that input, output, or the outside world was involved in mystery 2, but not in mystery 1. Okay. So the Haskell programs are pure mathematical functions, which means it doesn't have any access and the side effects. And what we mean by this is, if we have a function like y is equal to square of x, all right, that does not affect anything. It gives a value to y, so just say square. If I call that on square 4, it's going to make y is going to be given the value 16. All right, and that's what happens there. Nothing else is affected. Okay, so that's what I mean by the pure function. Nothing else. We know what it's doing and it's not doing anything. But we need to have, at some level, we need reading from the keyboard and writing to the screen or side effects. So if you remember in Java, any void methods that time were doing, the accessor, they were accessing state, or they were looking at the outside or printing something to the screen. It was all, anytime there wasn't a return type, even sometimes when there was a return type, there would be effects and side effects. So when I say they've no side effects, they have effect. The effect of a function is the value it returns. Okay, so interactive programs can be written in Haskell by using types to distinguish pure expressions from impure actions. Okay, so we still need to say this is where, we want to ring fence essentially where the outside world has any effect. So we have one type, and this is the type of an action. And this is the type of an action that return a value of type A. So you can have something that says, I'm talking to the outside world and I'm going to give you back an A. That could be, for instance, a list of lectures or a list of rooms or whatever, in your case, all right, if you're reading it in from the outside or whatever. So you could have IO character, and we'll see some functions that have something like that later on. Now this one is an interesting one, and you might recognize this from your main function. This type of purely side effecting actions that return no result value. So it just has side effects and it doesn't return a value. So like the main function doesn't return a value, it just does stuff. All right, because there's nothing to call it, it's not going to be called by anything as such. So your main function will have that type, and that's why we do it. So the empty brackets, they're tuples with no components. So what do we mean by an action then? So actions have the type IoT, and so it's really nice that we can talk about these as first-class values in Haskell, and they fit in seamlessly. Okay, so they produce an effect when they are performed. But not when evaluated. So it's a bit like the static and the dynamic type in the in Java. There's a difference there. So they'll produce an effect only when called by something else in the I/O context. So what do we mean by that? So what's an action? Okay, so an expression may produce an action as its value, but the action will not perform the I/O until it's executed. So literally, like it's like everything else. If you're not going to, if your I/O is to read something from the keyboard, you're not going to be waiting for that. It's just going to happen when you're calling it in that way. Performing or executing an action of type IoT, that's saying that the I/O doesn't necessarily mean that it has to perform the I/O, but it does have to deliver the result of type T. So I/O is saying we're leaving this open for speaking to the outside world. Because, for instance, you could have a conditional or anything like that. So we have actions of type IOA. We've seen that as being character, empty, string, whatever. And they're descriptions of effectual computations. So computations that you might have thought of as mutations, things that change things in the outside world, be that state or the outside world with print, reading from the outside world and so on. Because essentially in the outside world, you don't have full control. Something could go wrong there and you don't know when it's going to happen. So always you don't have the sort of control that we usually have in that. Okay, and if these are executed, they would possibly perform an effectual I/O operation, but it will eventually produce a value of type A. Okay, because it's if you like, the I/O is saying, yes, I may be speaking to the outside world, but I'm definitely sending back A. So I'm going to have an example here. So here we have an example of a cake. So that's a cake, it's pavlova. And alternatively, we could have a recipe of a cake. Okay. And that there is a recipe. That's actually Mammy Mara's recipe. She made a great pavlova. And so if you've got there, what you have is the ability to make the cake. So it's not a cake, but it's instructions for doing it. So you have the recipe. So not only do you actually have a cake, you don't have the cake, but just having the recipe has no effect on anything else. It's sitting there, right? So in the same way as before you call a read line or something like that, it's not going to have any effect. So it doesn't cause the oven to get hot, put all the ingredients in the bowl, or mix the ingredients. So to actually produce a cake, the recipe must be followed, ingredients bought, the whole lot, and the oven to get hot. Okay, so in the same way, a value of type IO is just a recipe for producing a value of type A, and it may have some effects on the way. Like any other value, it can be passed as an argument, returned as the output of the function, stored in the data structure, or combined with other IO values into more complex recipes. Okay, so here, I'm not going to play it now, but there's a video of the Swedish chef from the Muppets if you need a little break. And he's cooking something, and it's a little bit of a disaster, but there you go. These things happen. Okay, so the main function then, we've had that, and you've seen that in your first version of the assignment. How do values of type IO ever get executed? So basically, there's only one way. The special value is this main IO. So this is what gets handled at the runtime and executed, and that's it. Whatever you have in the main IO gets done, and that needs to be then that needs to be like the driver. It's going to kick everything off, and you'll see from the starter code as well that everything gets brought into that. And in the same way, you want to minimize the logic that's there, so the heavy lifting is done somewhere else, but that's kind of a separate issue. Okay. So think of the Haskell runtime system as the master chef. There you go again. And the only one allowed to do any cooking. So it has to go through main. Okay. Now, some actions that we have available to us. So get car. That reads a character from the keyboard. So we need an IO there. And it echoes to the screen. So it returns a character as its result value. And that's what it looks like. So this says we're going to need something from the outside world. And this says, now technically what it's saying is I may use the IO, I'm leaving that open, but I'm definitely, I have to send back a character. Okay, so that's the first one. So you'll be able to, we'll see how this gets incorporated later. So it looks like a value rather than a function, but it actually stores the IO action. So, and when it's performed, it just returns the character. So we have a special operator. It's like the left arrow, and it pulls out the result from performing the IO action. So it's quite a nice looking operator in the sense that, you know, it takes something in and it does a few other things as well, but it's only for use with the IO. Okay, next one, put car. Guess what this does? It takes a character, right? And so you're going to say something like put car, you're going to take a character and you're going to send it, hopefully using IO somewhere, but it's not going to return a value, it's just going to change the world. And by changing the world, I mean it's going to put the character on the screen. Okay. Now the return V you will need in certain functions, and it just returns a value V without performing any interaction. So it just, within that context, it'll just return the particular value. And so it takes an A. All right. So it takes an A and it gives me back an A in the context. All right. So sometimes you'll need, your method will expect an IOA and you only have an A, you'll need to send it out like that with the return. Okay, now the sequence of actions, we're going to see some code now in a couple of minutes. So the sequence of actions can be combined as a single composite action using the keyword do. For example, now this is, we need the outside world and we're going to return the characters here. Okay, so you're going to say do. So what we have here when we say do, is we have basically all of these in sequence. So this is the first time we've actually seen sequence in Haskell. Okay, so we do, this is what I was talking about, the this here. What this does is it waits, as any self-respecting reader will do. It's going to wait until you type in a character. It then puts that value, and remember what we said, that this takes whatever comes from getChar and puts it into X, but it's only applicable when it's an IO one. Okay. The next one you do a getChar, but you swallow it up, you don't care what's in it. So you'd be doing X, hit return, and then Y. So you're reading in two values, X and Y, and you're simply just going to return the XY there, and that's here. Okay, so you're returning the XY in that way. Okay, you don't need any return when there's nothing been returned, but if there is, you will need the return like that. Okay, the do notation is really important. Essentially, for most of the things you'll be using, your main function rather, will have a do, because you need to sequence things like that. So it gives us a way of building I/O, because in general you probably will need sequence for the I/O, because take in the data, then do something with it. So it does two things. It uses sequence I/O, and it also allows us to name values returned by the I/O action. Okay, and because the later actions might depend on the values captured earlier. Okay, and oops. Okay, so we might want to read a string from the keyboard. Remember the three basic ones were getChar, putChar, and return. So we want to use this to build up reading characters and returning a string. So you can see here we're saying, yes, I'm going to use I/O, or maybe I will. Now I know I do because I can see it, but I'm definitely going to return a string. Okay, so if I want to type something like cat, all right, okay, sorry, poor cat has gone away. We will, you can see what's going to happen. Just have a look here at what's happening. You're going to do a getChar here. All right, so X is now given the value of C. There's obviously a \n here, so that's not the case. So else do, now this is getLine. So what you're going to do is you're going to say, well, run getLine to get XS, and then you have your X from here, right? And put that at the beginning of what's coming next. So you see you're using the recursion here again, and you're using the recursion, and okay, So just have a look at that and convince yourself. So how does it get out of it? It gets out of it when x is equal to \n, and when that happens, you are putting XS being returned is actually going to give you the empty list, so that goes at the end here, and you're left with a string or a list of characters, and that will do that for you. It will return a string for you. Okay, so okay. We're just using the if then else there. Writing a string. So you can see writing the string to we're only given putchar, but of course, like writing a character isn't going to get us very far. So putstr takes an empty, because remember you need this way out, and it returns that. So you can see that's because I'm returning, and this says I'm not returning a value, but I'm ready to finish. Remember the return, it's the same idea. It terminates as well as doing that. So here you're saying, if I have a string with x and xs, I put, this is my basic one, and then I go at the rest. And I keep going at that until I've got to the end, and then I return that. Okay, so it's going to go line by line, character by character, and go from there. Okay, so if we want to write a line, or write a string and move to a new line, what we would do here is, what we're doing is we're using this. So this is the usual Haskell idea of building and building and building all the time on the previous written functions, or previously written functions. Okay, so putstr takes a string. All right, now it is the same type here as that one. So when you're calling this, you could technically just call putstring at the putstr here, and because it is the same type, it's okay, it's going to work. But you're actually going to you're going to print out all the characters in the string, but then at the end, before you finish, you're going to say putchar. So when this has finished the put string and printed out CAT, this will come, and before it finishes, because remember that will be returned to itself, and then you'll putchar n. And you know that putchar has a return type of, it has no return type or an empty return type. So that's still not going to have any return value there. Okay. If I just want to write a string out 4 times, I'm going to take that string, I'm going to say print it, print it, print it, and print it. Okay. Not very clever, but you can see what it does. So remember that you need to be really careful. These are spaces, not tabs. Now I think you can set it up in Visual Studio Code that the tabs are the same as spaces, but you'll get the strangest error if you put the wrong thing there. All right, so just if you have just put something in like that and you're just wondering what it is, always check the indentation, because it could be that. Okay, so we could read loads of lines. In this case, we're doing something that's kind of ridiculous, but we're just reading in that and reading in that, but we don't have our this here at all. Sorry, not that one. That we don't have that at all, so it's not actually going anywhere, and that's okay. Kind of has to be. Yeah. Okay, so and then all you're doing in the put string is you're saying 2 lines are red. I'm not going to tell you what they are because I didn't remember them. Okay, but that's it. Okay, So read lines is applied to arguments, but what we mean by that is these are the two values that are read in, okay? And they're the effect, that's the outside world is reading as in, is given as two arguments. Okay. If I want to get a line and print it, I can just do it like that. So what it does is now again, this isn't going to change the world for you, but you're bringing in the line and then you're just printing it out. So just to note here what this is, it creates a new variable. So this is a new variable now. And why do we have it? We have it because we need to be dealing with it later. So we need to give it a name and the usual meaning of a variable. The only thing is, it's an immutable object. Once you've set it up, you can't change it. That hasn't changed, but once you set it up, okay. So it acts as a local definition. So for the rest of the get input, you can use line. Okay. Now we can't change line because it's mutable, but what we can do is we can decide to do it like this. So here you have your two lines, right? And they're defined or assigned their values when we do our get line and when we type in the string. And then what we can do is this, reverse line 1 and reverse line 2. Okay. Now we will see later where we can be more sophisticated in the way we read that. So before we get it to line, we can actually do some processing. But for the moment, we'll leave it to that. Okay, so we can use local definitions, and the way, in the same way as we've done it before, the let is a local. The let is a local definition. Okay, so that says I have rev1 available to me from now until the end. Okay, and I'm doing that. Of course, I could have, as I did in the previous one, I could have said reverse, but as usual, it's nicer to name things if you're going to be using them a couple of times, but as well as that, even for clarity. Okay. And remember that it's only with the arrow, it's only with IO actions. Okay, so but just don't a really common error is when you say it, you're going, oh, I can see sequence again, I've hit home again, and yeah, so it's just about the IO stuff. Okay, and these are our local definitions. Okay, so this is the idea. Why do we do this, right? And the pure code ensures that Haskell functions return the same result when given the same input. So it's we don't want non-determinism means given the same input, we can't be sure it's the same output because there's other things coming. So the input could change, the file could change that you're basing it on, and so on, all those things. So in the pure function, same parameters, it's only about the parameters. So if you have your formula based on that, then it's always going to be the same. It could be, because remember our mystery in when we started out, never has side effects, the pure one. So it's literally y is equal to sine x or y is equal to double x or whatever. In the impure, it may have side effects. Now, if you have it as IO, it should have a side effect. You know, in most cases, there might be ifs and stuff like that. But because if it's not, you know, you don't call everything an IO just in case. As usual, you'll try and narrow it down as much as possible. It never alters state. It never affects the pure one. Never affects the outside world. But of course, this does. It could change state. We can do that using monadic programming, which we'll be looking at. and it could change the outside world by just printing something to the screen. Okay. Why does it matter? So in other languages, we can't be sure of no side effects. We need to read the documentation and hope it's accurate. But in this case, and an awful lot of bugs are caused by this, because if you have side effects, that means it's affecting something else. Now, the most benign version of that is that it's coming out on a piece of paper or on a printer or something like that, or on the console. That's benign because it's not acting as input into anything else. But if you're changing state in something, it can have a big issue on it. Okay, so it can cause cascading effects if you're using multi-threading or whatever. So it's like everything else. What we're trying to do is isolate the bits of code which help us. If there's a problem, we can isolate it very quickly. Anytime there's a couple of things can change, that can cause ambiguity in where the problem is. Okay, so isolating side effects into I/O provides really the best we can do. So it's a clear boundary between effects and potential side effects. So if we go back to our mystery in Java, we have mystery 1 and mystery 2. There's no, in Haskell, if we just look at this one, that's the same as before. Here, our two method headers are the very, very same, but one of them is taking information from the outside and the other isn't. And there's no obvious difference in the method header signature. If we look at a version of this in Haskell, the first one, clearly you're taking in two integers. There's your input, val1 and val2. And, you're returning one integer. That's it. Now, the fact that there's one hiding in the middle, it doesn't matter because you're still going to have the same answer every time. This one, the big red flag is here because you have your I/O here. So you're saying we have our do as well, and we're saying enter a number, so that's just to the user, and the get line here is val, so that reads in the val, and you're just going to look at that. Now we're going to have a look at this in a moment, but you see that read there. That read is a really nice function, because what it does is this takes a line, and what this does is it tries to make it to be an int. Okay, so we're going to assume it's an integer for the purposes of this. Okay, we have ways around it, but yeah. Okay, that's the int, and then we're going to say return val1 plus val2 plus val3 to the power of 2. So what this does is it changes a string to a number. And read, we'll see about that later, but basically it takes something of one type and changes it if possible. So clearly there's no I/O there, and there is I/O involved there, so it's very clear where the I/O is involved. Okay. We can now define an action that prompts for a string to be entered and displays its length. So this again is what you're saying is, yeah, I might need the I/O, but I'm not returning any value, even though it's not the main function, but I can do this anytime. But what you can see is that this is clearly just going to send something out onto the screen. And we just say, please enter a string, because we're very polite, and it enters the string here. And then we just say the string has and we want to say length S, okay? But actually the show here, if you remember, when we were writing put str or put string, that expected characters. And show is almost like a toString. So it's going to try and make a string from anything. In fact, it can do it. And we'll see how you manage that in the typing. We have another topic on types, and we'll be going through that in that. Okay, so this is saying I have a number, the length of XS is a number, but I actually need a string to go in here. So I'm going to do that, and then this is just characters. And remember what that does, we wrote it, it actually puts the new line at the end of that. Okay. And that's what that does. Okay. So evaluating an action executes its side effects with the final result value being discarded. I said don't return any value to me, so it didn't. Okay. We have a thing called Hangman. Hopefully some of you have played Hangman. And what it is, one player secretly types in a word and the other player tries to deduce a word by entering a sequence of guesses. For each guess, the computer indicates which letters in the secret word occurs in the guess. So, and the game ends when the guess is correct. We don't have a maximum number of runs or anything in this. So we adopt a top-down approach to implementing it, starting as follows. So we say Hangman is IO, which means I might need IO, and basically that's all I want to do. So I'm not going to be using this. I'm not going to be using the value that comes from this ever again. I just need something to be printed out. So think of a word, and we'll see sGetLine is a silent getLine, so the user can't see it. So the manager will type in the word, and then the player is trying to guess it. So we're going to say play the word. Well, what does that do? So play the word essentially is going to keep going until you match all of the letters. So this getLine reads a line of text echoing each character as a dash. Okay, so it needs to do two things. It needs to send back the string that it's made up of. So it takes in the X, and what it says is if the X is the end of line, just you don't need to add that to the string, but you're just going to put char X and return this, because this is going to be recursive, so you need to return that. Otherwise, instead of printing back out the character you've just read in, you're going to put out the minus on that, and then you're going to recursively call that again. And because you've just read X, you're going to return the line, this one. So you have your X here, and that's going to come down, all right, and your excess from here is going to come from there, all right. So see that again. So that's the recursive nature of that. Okay. So you type in something and it basically echoes it back. It echoes it back to you because of this. and the return. So kind of convince yourself that it has to return a string, you see. So this is when it's finishing up, it's returning the empty list, which is itself a string, and these are all characters. So that's a character, and XS is made up of characters as well. Okay. CH is get CH, read the single character without echoing it to the screen. So here, this is just a system call essentially that sets the echo to false. So when you print out a character, when you're turning it off, you're reading the character, but the character you've typed in isn't echoed on the screen, but you return the X. Okay, so you're returning the X here. So the whole effect of this is to try and read that, or to read it and return the X, but it only returns it internally. You don't see it on the terminal because this is sent off. But the minute you've done that, you turn it on, you turn it off, and then you immediately turn it back on again for the next person. Okay, you might be doing this in a loop, but don't worry about trying to set it back. Always set it off, set it back on in the end, and it keeps it. It's not going to have any effect on anything else. Okay, the main loop is this. Okay, so you're saying, play word. This is the word that you're bringing in, and this is the word that you're trying to guess. So you're saying, put in your guess. Now, if the guess is equal to the word, and that will happen if the two strings are the same, you're going to be delighted, and you'd say, you got it, and you're gone. Okay? Otherwise, now we have a new thing, put string. Well, what is this? This is actually another function that takes the word, which is the word that the manager or the gameskeeper typed in, and this is your guess. And what that's going to do is it's going to, any of the letters that you've guessed will be typed in, and any of the letters that you've left out that you haven't put in will be there as your dash. And then, because you haven't solved it, you're going to play the word again, exactly the same. Okay, so you would hope in that case that you would put in a different word. So what does match do? Okay, so this is really nice using using our list comprehension here. So we have XS and YS. Okay. Now, if we look at the way it's called before this, sorry. I'm looking the wrong. See the way the match is called. Remember this. So this is the word you're looking for, and this is the guess. The word you've just typed in as your guess. So, okay. So this is the word you're looking for, and this is your guess. So what you're saying is, look at X here. Okay, look at XS, sorry. This is the word, the correct word. So you're going to say, give me the first letter of that. If this letter appears in YS, then type X. So we'll see how this works. Otherwise, dash. And do this for every single time. So what you're doing is you're producing a string that will either have the letters of the first one or nothing. So we'll just see how this is called then. So I would call this as Haskell. So this is this is my XS. And this is my YS. Okay. So when I look at just say the first one, I'm going to say H. Does H appear here? It doesn't. So I'm going to print this. Okay. The next one is A. Does A appear here? And if it does, I'm going to print A there. Okay. So it's just all the letters from Haskell that appear in the guess you're going to get there. Okay. And S then is here, so that's there. K and E aren't in Pascal. L is, and L is. Okay. So have a look at that. So again, what you're saying there is you're taking each letter from Haskell and you're saying, does that letter appear in Pascal? Okay, so the first one, it doesn't. So you're going to, the first element of the string is going to be that. Because remember, this is list comprehension. So the list comprehension says, when you take out an X, that X is either, the new list is either going to be an X or it's going to be this. It's going to be an X if that appears in that, otherwise the dash. All right. So that's actually the way the hangman roll. So have a look at that. It's a kind of a nice example of a kind of a nice simple kind of game. And I've got now. We mentioned this the last time, and it's the read with the function. So what read does is it takes an A. We'll go back to read in a minute. Of type A. We take a string and we return an A. So basically, if we're setting up a new type, but generally things like numbers will have that, and so it takes a string that you're getting in from the outside world and it tries to change it. It tries to change it to whatever you're trying to. So in the one previous, we wanted to change it to an int, so we will try to do that. Okay. We'll come back to that when we're setting up new type classes. It'll become more obvious. And a parse a string representing a value into that value. So remember again, it's the whole idea of what types are. We're reading things in as strings. So if it's a series of digits, it's still not a number. It's just a string. So if we want to be able to do the number things on it, we need to make it into a number, and so we transform it in some way, and this read will do this for us in as far as possible. Okay. So an example using read. Okay, so we have our get line, and we've seen it before, but just to go through it more. So we have the string, and we need to sequence this with an IO action to return the line interpreted as an integer. So we're going to see how it's done, and here. So now the big thing here is I'm returning an integer. Okay, if I was just returning a line, it would be a string. So what I'm trying to do here is I take the line, which is now a local variable, and here okay, so how does read know what to return? Well, read is very clever, and read knows that you're returning this, it's expecting an integer, so it will try and change it into an integer. Okay? So, when somebody somewhere was defining integer, it would have put, we see that it knew it needed a read on it. Okay? So, now it doesn't need a return, okay, because it's a value. So it says, you promised me a value back. Oops. Promise me a value back. So I'm going to send you back a value, but here it says, now make sure it's an integer. Okay. So the compiler can figure out that it's an integer from this. Okay. So, more generally, remember that read A, that's the type of read. So we can specifically decide what type we wish to cast. So you could say read the string 1 as an int, or inside into do block. We that's the way we started a couple of times ago, right? Okay. And adding now show is the opposite. Again, we'll be doing a little bit more on this, but it's important you know this. If you want to add two numbers and print a result, now we need to read it in as a character, make it into a number, or maybe not, but definitely if we're sending it back out to be used as an integer, we want to do that as well. So here, if we want to return it or use it as a character. So here, we take in the two lines, so they're the two numbers, but all we have is line. So here, or get line. So here we're saying, make this, give me back an int. Make num2 an int. Now, we will later look at what happens if they're not digits, but for the moment we'll do this. So now we have the integers and we can add them. So this is what we're going to do here. Great, we've added num1 and num2, but remember this needs to be a string, and you know in Java it's good, it can kind of figure out what's going on, but here we need to say this needs to be a string. So the show will make it into a string. Okay, so show will take any type if you've set it up like that, and it's automatically set up for most of the given types. Okay, the reason I'm saying that is you will have situations where you'll need to implement it. Okay, getInt uses read. So you can see here, same idea here. You're saying the sum is show that. So getInt already uses read to make it into an integer. Okay, so there are your references there, and you can have a look at those. There's quite a lot in some of those. Programming Haskell is what kind of gone a little bit away from it, but it's mainly the thrust of the whole course, and there's some nice things in the get programming, and the middle one there is a course, and some of the ideas from this lecture were based on those. Okay, so that's interactive. We will be doing a little bit more. Well, we've seen what read and show do, but when we're creating new data types, we will see how we bring read into the equation, if you like. Okay, so sorry, this is a particularly long one now, and I will talk to you later, but for the moment, if you have any issues, just drop something on Slack for me. Okay, thanks a million, folks.